Well, I think you can see from the title that this is going to be a pretty important nugget in this particular course. It's a nugget on IPv4. By the way, this is not the only nugget on IPv4 that we're going to have. There's going to be more focused nuggets on different areas of the IPv4 protocol suite. In fact, I just said protocol suite. Let's start out here by taking a look at the overall protocol suite that we have with TCP/IP version 4. So when you look at the TCP/IP protocol suite, you realize just how much there is to learn. Notice how this is organized. We've got the OSI model layers here, and then we've got the TCP/IP model layers here. DARPA refers to the organization that helped create that model. So we have these various protocols that are in the TCP/IP protocol suite. And here's the deal. This is not an exhaustive list. So this is just a handful of the protocols. And it's kind of a nice look at some things that we're going to be focusing on. For instance, I'll have a nugget dedicated to IPv6, which will just scratch the surface, by the way, of that particular protocol. We can see things like frame relay and ATM down here at the physical and data link layers. We see the address resolution protocol. And one of the things that we'll be focusing on big time in this particular nugget is the IPv4 addressing at the network layer. And I also want to focus on connection-oriented transport layer work like transmission control protocol and non-connection oriented or connectionless communications at the transport layer with something called user datagram protocol. So IPv4 addressing, TCP, and UDP are really going to be key focuses for us in this particular nugget. Now, I probably don't need to tell you that an IPv4 address is 32 bits in length. And to be readily recognizable by us humans, we use a dotted decimal format. So an example of an IP address would be 192.168.0.1. The subnet mask is done the same way. We could go 255.255.255.0. This is the default, let's see, 8, that would be 16 24-bit mask for a Class C address. You see, they decided to organize the address space into classes. So let's start with a Class A and make sure we understand everything in this table. Boy, can I create a lot of flashcards from this table or what? Could the exam, for those of you interested, ask a lot of questions about this? Yes, indeed. So Class A starts with a 0 in the first bit position. That's the leading bit field. Then there are 8 network bits. So right away, we know that the default subnet mask for Class A would be this. That's the default subnet mask, indicating that the first 8 bits, as we see here, identify the network portion of the address. The rest of the bits here, the zeros in the subnet mask, identify the host's addressing. Pretty cool. So think about a Class A, let's say the 10 network. We could start addressing hosts at 10.0.0.1. And then the next host on the network could be 10.0.0.2. You get the idea. The number of networks that we can create is 2 raised to the 7th power, or 128. So we can create that many networks. Pretty cool. The addresses per network that we can accommodate is 2 raised to the 24th power, or 16 million addresses. You can see that when the designers of IPv4 set up the addressing, they figured there was more than enough addressing to go around. They never anticipated the explosion of the internet, right? Total addresses in the class, 2 billion something. Again, hammering the fact home that they really thought they had enough addresses to go around. It starts with the quad 0 address, although you can't use that one, and it goes up to the 127 address, although you can't use that one either. Those are special purpose. The 127 is reserved for loopback. In fact, let me show you that real quick on like a Windows PC, for example. The loopback address is automatically assigned to my Windows device so I can test TCP/IP's basic functionality on my device. I'm guaranteed to be able to do that. If IP itself is working on my device, I can ping, I can test contact the 127.0.0.1, for example, and it says, yes, IP is here, it's alive, and you can communicate with yourself utilizing that loopback address. Pretty cool. So notice here I gave an example of a 10 network in the first octet, and that fits within this range, so it is indeed considered a Class A network. We move to the Class B network. The Class B network has the leading bit positions forced to 10. There are 16 bits that identify the network and 16 bits that identify the host. So it's divided in half. So it would be for a subnet mask 255.255.0.0. 16 bits identifying the network, 16 bits identifying a host on that particular network. By the way, we get kind of fatigued writing out subnet masks like this, so a really cool way that you can write them is called prefix notation, /8, /16, just indicating the contiguous bits that are set to identify the network. So I might say, hey, yeah, man, my address is 10.0.0.1/8. That's a cool way to say it. None of that was cool. And I don't know where I got that weird voice from. Just forget that even happened. Okay, so how many networks can we have? Well, 2 raised to the 14, roughly 16,000 networks. We can have 2 raised to the 16, 65,000 hosts per network. We can have a lot of addresses in that class. We start at 128 and we go to 191. Do you have to memorize some of these facts, like the starting address and the ending address? You do, because a favorite of the exam would be to say, hey, your address is 164.10.8.14. What address class is that? So you'd have to know that 164 in the first octet puts you in the Class B range. The Class C range starts with 110, 24 bits for the networking, only 8 bits for hosts. The default mask would be 255.255.255. 0/24. Oh, no, not /24, but that's how you could recognize it, right? Instead of writing it out like that, you could write /24. So that's an alternate representation of that subnet mask. We get a whole bunch of networks, like 2 million of them. We only get 256 hosts per network, and you can see the total number of addresses, the starting address, and the ending address. It goes from 192 to 223. Class D are multicast addresses. They start at 224 and go to 239, and then they reserved for experimental purposes from 240 to all 255s. We don't use those. As a matter of fact, we do use this address right here. This, of course, is the broadcast address. So some of these addresses are reserved for special purposes, but this gives us a great look at the address classes. And as I said, there's lots of facts for us to kind of mine from this table, and I'll have lots of flashcards that are going to help you with this. Now, when there started to be an address shortage, the engineers in charge of this stuff said, we better take some of these address classes and we better pull them back. We better take them from the community at large and we better mark them as special purpose. Specifically, these are called the private address ranges. So 10/8. Notice that's anything that begins with 10 for an IP address is private. 172.16/12, that ends up working out from this address to this address. And then 192.168.00/16, anything from here to here. If your address falls in this range, it is private use only. And the whole world can use these. So you have all of these pockets of private use, and they are NAT, network address translated, if they want to go out to the public internet. So if you look at your home network, you're going to have an address in one of these ranges. The most popular for home networks is one of the 192s. And then there is network address translation done by your device so you can go out and communicate on the internet. Now, as we move up from the network layer and the happy IP addressing, we get to the transport layer, and here we can make a key decision. That was the weirdest thing I've ever drawn on a slide. I don't know what I was trying to do there. The transmission control protocol is our connection-oriented, and UDP is connectionless. The analogy that I have here is TCP is like you and I making a phone call with each other. There's reliability, and we do things to make sure of like error checking. Like if I don't hear from you for a few minutes, I'll say, "Are you there? Hey, are you there? You still there? Can you hear me? Can you hear me now?" I think that was a famous commercial, right? A national commercial campaign for one of the major characters. Can you hear me now? Can you hear me now? So we're doing all that error checking to make sure the connection stays beautifully valid. A UDP communication is more like a postcard. We hope it gets there, but we don't do anything to check and follow up to ensure while it's in transit that everything is okay. So one is connection-oriented, we babysit it, TCP, the other is connectionless. Now, this is where students typically say, my goodness, why wouldn't you always want TCP? Mike, you always are going to want a good, reliable connection, and one of the things that uses the TCP protocol is HTTP. That's why web surfing works so well. We make a connection up to a website, we get all the texts and all the graphics and all the movies and all the sounds from that website, and it's a beautiful experience, and typically it works perfectly as long as your internet connection isn't having problems, and it's happy. Why wouldn't we always want that kind of a web surfing experience with transmission control protocol? Well, the answer is really speed and overhead. Yeah, there's a very little overhead, which means for high rates of speed when we utilize user datagram protocol. A lot of audio and video applications would use it. Some other protocols that use it are the trivial file transfer protocol. We don't want slow, we want fast and efficient, so we use TFTP instead of FTP. DNS will default to the use of UDP for efficiency. Simple Network Management Protocol will use UDP. DHCP likes UDP for efficiency. The silly little very basic routing protocol called RIP, Routing Information Protocol, will use UDP. So lots of things will indeed use UDP for the efficiency compared to transmission control protocol. There is so much that goes into transmission control protocol to make sure that things are done right. Like segmentation of traffic is done to make sure it's of a size that's going to fit on the wire. Sequence numbers are used so that we make sure we're getting things in the right order. Once you get a bunch of segments, you will send an acknowledgement back to the sender saying, yes, I got everything in the right order, everything is splendid. So this is a theme that we see throughout networking, by the way. Some protocols like PPP act like transmission control protocol and they're reliable. Other protocols are unreliable, they're connectionless, and they act like UDP. It's really pretty cool. Let's bring this to life as we wrap up this particular nugget. Let's bring this to life by going over to Wireshark and seeing if we can catch some TCP versus UDP traffic. So I'm going to fire up Wireshark here, and I'm going to go up to the capture menu, and I'm going to go to interfaces, and I'm going to say, let's capture my local area network connection. And here go those packets. And look, I'm going to go ahead and stop this because it happened almost right away. If we scroll up to the top here, we got a UDP packet. And then we got a TCP packet that was captured. By the way, I want to tell you again, we got plenty of great courses here at CBT Nuggets on Wireshark. I think Keith Barker did like all of them. Keith Barker's awesome. You'll want to check out those Wireshark courses for sure. Let me double click this UDP packet here and let me resize this so we can see it all. And what we're going to discover is when we go to the UDP header information, there's like nothing. I mean, this is unbelievably simple. It gives you a sense for the lack of overhead that we have with UDP. There's a source port identifier, there's a destination port identifier, there's a length, and there's a checksum. My goodness. I mean, it's really like source and destination port, right? That matters to us there. That's it. Talk about efficient. Now, when we go to TCP, we're going to get a lot more stuff going on, and that's by design to ensure the connection-oriented nature of it, to ensure the reliability. Look at this. We've got source port, destination port. We've got sequence number, acknowledgement number, header length, window size value, a checksum, an urgent pointer. So lots of stuff going on. What's the window size all about? That sounds interesting. Well, there's this concept of sliding windows where a machine will send the TCP information and it will try and send a whole bunch of it. And then when it gets acknowledged, and that was fine, it'll say, all right, I'm going to send even more in a send window, in a send length or amount, if you will. And then if that gets acknowledged, oh, cool, I'm going to try and send even more. So it's trying to make the communications of transmission control protocol more efficient by allowing us to send more traffic without it having to be acknowledged, because the acknowledgement's going to slow stuff down a little bit. So notice there's a lot of overhead in transmission control protocol, but there are mechanisms within TCP that try and mitigate the effects of the overhead as much as possible. So in this nugget entitled IPv4, we took a look at the IPv4 protocol suite with a particular focus on two areas: the network layer, and our focus was on addressing big time, and of course the transport layer, where we saw applications can rely upon two different strategies. A connection-oriented strategy, like in the case of World Wide Web traffic with transmission control protocol, or on the other side of the equation, connectionless, like simple network management protocol with its utilization of the user datagram protocol. So much to learn. But the great news is we've got plenty of time. This is not a race. I sure hope this nugget was informative for you, and I'd like to thank you for viewing.